Let's say you want to determine the charge to mass ratio for a given particle. You accelerate the particle through a potential difference delta V. The particle starts from rest, and when it reaches the end of the potential difference region, it is moving at speed v. And then it enters a region of magnetic field where the magnetic field is uniform and it's perpendicular to the velocity of the particle. So what does the particle do? Now it's going to follow a circular path of radius capital R. And let's say you're able to measure the radius of that circular path, capital R, and you know the potential difference that you applied initially. You plot delta V against R squared and you obtain a straight line. The question is, what is the charge to mass ratio for this particle if the magnetic field has magnitude 0.34 Tesla and the slope of the best fit line is equal to 8.2 times 10 to the 5th volts per meter squared? How can we solve this problem? Now let's take a look at what's going on as the particle is accelerated through the potential difference delta V. Now what happens is that the electric potential energy that the particle initially has turns into kinetic energy eventually. So then the initial electric potential energy is equal to the final kinetic energy for the particle. Potential energy is equal to Q times delta V, and kinetic energy is equal to 1/2 mv squared. We set the two equal to one another. After having accelerated, the particle enters the magnetic field region and starts moving in a circular path because the magnetic force creates an acceleration perpendicular to the direction of motion, perpendicular to the velocity, so that causes a circular path. So we can apply Newton's second law here. Magnetic force is equal to mass times radial acceleration, and magnetic force is equal to Q times V. That's the magnitude of the magnetic force, of course. And radial acceleration is V squared over R, V being the speed of the particle, R being the radius of the circular path. So when we set this up, we see that there is some simplification, right? We have QVB equals mv squared over R. So we can divide both sides by V and simplify, and then combine the equation that we have from the previous part. Basically, the common variable here is V, the speed of the particle. So this will cancel, and this square here will go away. So V is common, and this is a variable that we don't know. We don't know the speed of the particle, and we're not looking for it. So let's combine the two equations to eliminate V and put it in a form that we can use to solve for Q over M, the charge to mass ratio. Here I have isolated V, and I'm going to substitute it right here in the equation that involves the two energies, and rewrite, so that way we will have eliminated V and we can rearrange the equation that we will obtain to serve our purpose. Here's what we get after the simplifications. So we can see that if we plot delta V against R squared, the slope of the best fit line will be equal to Q times B squared divided by 2M. So this is our slope. Now we can solve for the charge to mass ratio and substitute the numerical values. We get Q divided by M equals 3.5 times 10 to the 7th coulombs per kilogram.